அனைவருக்கும் வணக்கம். I'm Jagadeesh. Now my presentation topic is about Zeeman Effect. First we know about the Zeeman Effect. The discovery is interesting thing because the discovery was happened before the discovery of electron. At the time of 1902, physicists really didn't know what is electron actually, but so it is one of the astonishing experiment of all time. Still we using the Zeeman effect to calculate the magnetic eye ratio of an atom. About Zeeman effect, just we can simply describe in the two lines. Zeeman effect is the displacement of energy level gives a uniformly spaced multiple splitting of spectral lines is called Zeeman effect. Zeeman effect is correlated with many of the physics concepts like Schrödinger equation and hydrogen concepts and atomic structure concepts. We want to understand Zeeman effect correctly. We have to understand the Schrödinger equation, hydrogen concept and atomic concepts, because all are similar kind of it, all are spiral with each other. Now I split my presentation into two parts. First part is experimental part and the second part is theoretical part. First part we learn about how Zeeman effect apparatus really useful for the theoretical part, and the Fabry spectrointerferometer is used in many spectrometers, and it's also using in the atomic absorption spectroscopy. So in Zeeman effect apparatus we still using Fabry spectrointerferometer. Friends, just look into the magnet lamp. Magnet, there's a two magnets or in the middle of the lamp. And second one is a power supply for the meter, and third one is a focusing length, and fourth one is a polarization filter. This is the responsible part for the color of the spectrum of the interferometer, and the interference filter to give the clear cut image, and Fabry Petro Etlano, it's a dash name, and later we discuss about clearly. We already studied this in the optics in our second year, and another is a seventh one is a camera, or we can use microscope to see in our naked eye, but nowadays we using camera to capture the image. And it is a total bench for the setup, and ninth computer, we well known about it. And I just add a real-time image of experiment what I used to understand and explain the apparatus of the Zeeman effect. This interferometer makes to use a multiple reflection between the two closely spaced, partially silvered surface Atlano. So partially coated silver is used in the Fabry-Petro interferometer. So I just told that the magnets, yeah, yeah, we place a sample lamp in the between of there. I just pointing out on upper side, and this is the power supply for the magnetometers, and this is a cross section schematic diagram, and this is the Fabry-Petro interferometer's lens. Fabry-Petro Atlano, partially silver coated glass plates. When the incident rays enter into these glass plates, that's no ref- refractions happen, and so the continuous rapid zigzag reflections and refractions happens in the between region of the partially silver coated glass plates. So it act like as a grating, and it produce a multiple reflected rays out to the concentric increment. So we using in concentric lens to form a concentric circle in the higher order towards is the midpoint, and the increment of the circle is noted by the m1 and the m1 plus, and the condition for the maximum is 2d cos alpha is equal to m lambda. So we already learned this topic in our first year, so I just recall it, sorry, second year in optical physics. So I just recall it for the better understanding of the interferometer. Yes. And just we start the theoretical part of the uh, Zeeman effect in hydrogen. When an external magnetic field is applied, short spectral lines like n is equal to 3 to the true transition of the hydrogen split into multiply closed space lines. First observed by the Peter Zeeman, and its theoretical parts are done by the Lawrence. And n is denotes to the principal quantum number, and ml is denotes to the magnetic quantum number. When we look into that, the spectral lines down from the n, the magnetic quantum number of 2 and the principal quantum number there is 3, it's directly down moving to the 1 of the magnetic quantum number. But if it's ml is equal to 1, it have two possibilities, like it can move 0 or either 1, and if ml is equal to 0, it has three possibilities to move 1, 0 or -1. But if ml is equal to -1, it has two possibilities. It can move 1, -1 or 0, and if ml magnetic quantum number is equal to -2, it can reduce its energy level to the so to say that magnetic momentum to the -1. And so I just added the diffraction image of creating of hydrogen atom. So without magnetic field there is only one slit is present that, and on we on the magnetic field there is three slits are produced. In hydrogen spectrum. Yeah, just we see about the violet regions. Um, Violet region is n is equal to 2 2 and more than 4, sorry, and 4 to n is equal to 2 is for the blue green, and n is equal to 1 to 2 is a red light in the wavelength. So there's a the energy level, the wavelength is of the red light is 656.3 nanometer, and blue green is 486.1 nanometer, and visible region, invisible region, but violet violet's wavelength is 410 nanometer. From the beginning point is 484.1 nanometer. And also Bohr's model is also I given to express it. Now we not need it, but we have not understand it. This is the derivation part. So the Zeeman interactions. When external magnetic field applied to the dipole and the magnetic potential energy, which results in is a magnetic potential mu theta is a magnetic potential energy. U theta is equal to minus mu into B. B is a magnetic field, and mu is a orbital angular momentum. So we know the orbital angular momentums equation. We already derived that in our classroom. Mu orbital is equal to minus E divided by 2 em into angular momentum. Yeah, into angular momentum. The magnetic field in the z direction is given. Mu is equal to E divided by 2m. Lz B is equal to ml E h cross by 2m into B. So B is a magnetic moment. So we know that at Lz is equal to m small m L h cross for the total angular momentum. So we just add that portion into this equation. Considering quantization of the angular momentum is give equally spaced energy level displacement from the zero field level. Del E is equal to ml Eh by 2m. B is equal to ml mu B into B. So orbital magnetic momentum with respect to the magnetic field is mu B. So we know that what is we can able to calculate mu B by the Bohr magneton, and mu B is equal to E h cross by 2 m E. So the calculation part I just added this, and del E is equal to ml eh cross by 2m into b. So we are seeing the displacement of energy levels in these derivations are uniformly placed and splitted. So this is spectral lines are called the Zeeman effect. Also interact with the electron spin. And so it is contributes to the Zeeman effect. In many cases, the electron spin had not been discovered at the time of Zeeman's original experiment. So the case where the contribution were considered to be the anomalous, not normal term. The term Zeeman effect has persisted for the case where the spin contributes. Generally, both orbit and spin momentums are involved and the Zeeman interaction takes the form. So del E is equal to E divided by 2m into the vector quantities of L vector plus 2s into B is equal to GL mu B and mj B. Small gl is a magnetic eye ratio and mu B is a Bohr's magneton and mj is a magnetic quantum number, total angular momentum quantum number, sorry, into B. B is a magnetic field we apply into the normal Zeeman effect. In this type of splitting is observed with the hydrogen and the zinc singlets. So the magnetic field, so we already see the starting of this lecture. So singlet, this type of splitting is observed for spin zero state, since the spin does not contribute to the angular momentum. For magnetic field, on Tesla, we calculated, I added the calculated value for del E is equal to ml mu B and B is equal to 5.79 into 10 to the power minus 5 electron volt. Zeeman effect for hydrogen atom is offered experimental support for the quantization of the angular momentum which are arise from the solution of the Schrodinger equation. Anomalous Zeeman effect. So the anomalous Zeeman effect is really the normal Zeeman effect when the electron spin is included. So we have seen, we have saw in the derivation part, we are adding the finally we are adding the vector quantities like capital L vector plus S vectors. S vector is responsible for the spin quantum number. Electron spin is included. There is the greatest variety of splitting of patterns. Sodium Doppler, the field of and field on. There's more than 4 spectral lines in the on grating and more than 4 spectral lines are presented in the another grating. So totally 10 spectral lines are presented. The sodium doublets and zinc sharp triplets. Yeah. So for the zinc triplets, there's more than many spectral lines are we saw in zinc triplets. Oh, bravo. Interferometer image of the spectrum of sodium doublet. This is the real-time image. We're using different kinds of filter to forming the different colors of the spectrums. So spectrum colors depends upon the what kind of filter we use. So thanking to all of them. Sorry for making mistakes at the time of speaking.